Okay, welcome everybody. Let me start by reminding you what we were working on. We were looking at the problem of learning with functions using two-layer neural network. And let me remind you, since the setting, what is a rich function is a function f star of x that has the form u star of x. So it depends on one-dimensional projection of the data, and here our setting was x was a point on the sphere. U star is a norm 1 vector, and we assume that we are given data xi uniform on the sphere and yi equal f star of xi. And data points. Well, in fact, we are looking at online SGD, so as many data points as step sizes. And we're trying to learn it by minimizing square loss for the following neural network model, f of x. It depends on first layer, second layer weights, and first layer weight. This was 1 N, and that's well, sigma u1. And what we argued, so we looked at SGD, for online SGD for learning it, and what we argued is that in the limit of for large n, and so for large number of neurons and small step size. So large number of neurons means large, but compared to 1, but not compared to the dimension. Sorry, a small step size instead means step size much smaller than 1 dimension. Then this online SGD could be described either by PD or equivalently by an evolution over the space of function. And the last thing that I gave you is the formulation as an evolution in the space of functions. And this was what was the formula. Let me rewrite it for you. This is theta minus integral u and okay. Here the list. And here the unstacking is the dynamic system for the variable AT and UT that are functions. AT is a function from the interval 0, 1 to reals, and UT is a function from the interval 0, 1 to the unit sphere. here we're looking at this network with first layer will be normalized. So this is an evolution that is a parameterization invariant. Namely, if IPT-UT is a solution, then you can construct other solution by composing these with any similar thing. Well, okay, F is not a good name. Call it H. H is 0, 1, 0, 1. Measurable with its inverse. Okay, this is just a consequence of the invariance and the permutation of the neuron. Okay, so now, what is the real interest of constructing these, large network size limits or studying these large wide network limits? I think that technically the real advantage that you get, or the real boost that you get, is that you can exploit invariances, right? So group invariances. In particular, here, if I initialize with the UI, so we want to initialize with initialization the neural network where the UI are uniform on the sphere. Okay, and AI are IID with some distribution. Now, since the target function is invariance under rotation around U star, you imagine, so there is an invariance under we write OD divided by, so this is OD minus 1. So this is rotations that U star fixed. And this invariance is not convenient to exploit at finite n, right? Because at finite n, this doesn't simplify much things. The joint distribution of all the neurons is invariance, but this is invariance under the distribution over n objects. So this is very difficult to treat. While the position, if you treat the positions as deterministic, then since the initialization breaks this invariance, then you're in bad shape. On the other hand, here you can start with the initialization that is invariant. So we initialize with U0 and A0. Now we said that the initialization should be such that the push forward of the uniform measure is PA and push forward. Okay. This jointly, of course. So if you this invariance kept, distribution is invariant of the center rotation, and this remains true at all times. So if you work out the consequence of this is that if you want the rho t, the joint distribution of A and U is invariant under the same group of T. And therefore I can, this implies that I can write an evolution. So a consequence of this, the root is uniform, conditional on A and product of U and U star. The only thing that matters is the second layer coefficient and the projection of the first layer coefficient. So I can rewrite versions of these equations for these two objects. So I can write all this S, and perhaps what I do is just I'll replace this equation. Replace this equation by an equation for S. Okay, so let me write those equations. Here I will have D of S. And here I will have minus integral. So let me call it, let me explain what this is. Here there will be an equation for S. Because of the projector, here there is something that comes out is a factor square root of 1 minus S squared. Here there is, this gets replaced by B prime S. This is all evaluated to bigger. And this gets replaced by tilde prime, meaning the derivative with respect to the first argument, the S, D, G, U, D. Okay, so now we have a reduced dynamical system for these two functions A and S. The two functions are A, T, and S, T. Functions are 0, 1, 2 reals. Really, ST takes value plus minus 1. And what is this U tilde? Well, remember U, before we had an object that was potential that depends on U1, U2. This I remind you that expectation of sigma U1x, sigma U2x. So now if you think of this, right, what is this? So it's a function only, and it was a function only of the scalar product, I remind you, because X is Gaussian, so these are two Gaussian random variables with covariance 1, the product of U1 and U2, the product 1. So now, if you think about U1 and U2 are going to be unit vectors that are uniformly random, subject to their scalar product between, with U star to be S1 and S2. Okay, so this means that this U tilde of S1 and S2, okay, what's going to be the scalar product? This is going to be the expectation of U. So the scalar product is going to have a component that is the component along S star. So there is S1, S2, right? And there is another component that is the component orthogonal to S star. So these are the components orthogonal to S star are two vectors of norm square root of 1 minus S1 square, square root of 1 minus S2 square. So it is square root of 1 minus S1 square 1 minus S2 squared. Okay, fine. Okay, and then there is the scalar product. Now there is the scalar product of two unit vector in d dimensions, in d minus 1 dimension. So you can fix one, right? You can fix one of them to be E1. All right, so the second one will be, let's write it like this, E1 first times Z. And the expectation is over Z that is uniform in the sphere of d minus 2 dimension. Now I brought a reduced dynamical system, and now it's a dynamical system for just two functions. Two functions, but infinite dimensions, but it's much simpler than before. The idea making approximately apart from the n large and step size small idea making. Any question about this? Now I'm gonna look at large dimension. So I'm gonna, yeah.
Very stupid. So the invariance. Now, okay, the invariance equation you can also take by this class. H of omega 1. So you just take the equation, you parameterize and then. I mean, you
Yeah.
see it from the beginning, but on the equation, okay, I guess.
But no, the inverse under tranquilization, under rotation is really that you rotate. If you look at your UT, your guy. Okay, I should have done it before changing. But if you look, for instance, at DT, let's say that you look at DT UT, right? This has a bunch of terms, right? The first one was they use you stuff, right? Right. So what is invariance means that if R is in the group, right? So let's call it, I don't know how to call it, let's say GU star, so the subgroup of rotation. So R is an orthogonal matrix, right? It's a whatever orthogonal matrix that keep U star invariant. Now, if I multiply, so what you want to claim is that this is a solution, right? Then U bar that is RU is also a solution.
Yeah, but I think this, if I look at the previous equation, there is no derivative term with respect to omega anywhere. So this doesn't involve any derivative of h of omega. And because if it were the case, then you need to have some regularity in h. There is no derivative. Can I see the invariance?
I mean, the invariance is really, but invariance is the rotation. So under the parameterization invariance, yes. But
yes,
there are two things, right?
Yeah, no, I was thinking about the parameterization.
Parameterization invariance, yeah, it's simply the fact that yeah, you change.
Yeah.
You do a change of variable here.
Yeah.
Is that you do a change here, and you can reabsorb it in the change of variable. This and the variance of the rotation is going to apply this.
This is okay.
Okay, so now I want to take, therefore, so here, and okay, I didn't say what is the initialization for this. So I brought now the for A and S, and initialization would be that A0 push forward of uniform is whatever law you put in second layer way, and S0 push forward of uniform is what? Well, it's the law of the projection along, U star, so along any direction, will be one of the uniform vector on the unit sphere. Whatever you get. So roughly speaking, is very similar to a Gaussian of variance 1 over square 1. Okay, so this is order 1 over square root of t. This is of order 1 over square root of t. Now I want to take the d to infinity limit. And in the d to infinity limit, what you get is basically you can drop this term and you can replace this by 0. Okay, now I'll stop writing the argument omega, but all of this is evaluated at omega. And now we have a completely dimension independent system, and we want to study what is the behavior. This and initialization now, since I took d to infinity, the initialization will be that s0 is the function 0, and at is a function a0 that is a function that satisfies this.
Andrea, sorry, if I understand correctly, S is the scalar product of two unit vectors.
Yeah, it's the scalar product between the weight of my neuron and the two functions.
Okay.
Which the two functions.
So it should be bounded by 1.
Yeah. So it's
And do the equations preserve this bound?
Because there is this, you see, the speed, as you get it to 1, this pushes it.
Okay. Okay.
The speed gets. All right. Actually, I'm not sure whether here there is square root. As you see, it doesn't matter in the analysis data. So that term doesn't play much at all. Right? So the situation is that you start with these neurons and they are basically time 0, S is or close to 0. Here there is 1, minus 1, right? Within the neural tangent theory, they stay always orthogonal to the true direction, and this is why you don't learn anything. One way to escape is, now what we want to understand is how they develop something non-zero, some projection. Which stuff that's. So what we are going to do here is, to analyze this equation is we're going to exploit the fact that this parameter epsilon is small, and as you see, if epsilon is small, things happen in stages, in phases, and at each phase, a new part of the function is learned. Okay, so we'll explore it. Epsilon. So So there will be multiple time scales. Depending on epsilon. And will match between these different time scales. This is something that is often done in statistical physics, and kind of ODE or PD theories use this method as matched as asymptotic expansion. Now, from a rigorous point of view, there is some open problem here. We can treat rigorously every single, a special model in which only one time scale exists, but we cannot rigorously chain all of it up. But this should be the case for some non-trivial set of integers. So the first step to do this asymptotic expansion is to do an Hermite expansion, Hermite decomposition of these equations, because what will happen is that each Hermite term matters on a different time scale. So what is the Hermite decomposition? So we will decompose our target function, p of x, as sum of k times Hermite p of x, where this is the orthonormal, and the same for sigma of x. And what happens, so Hermite is important because what happens is, of course, that, for instance, the V, remember that is, the correlation between phi and sigma. So what happens is that Vk is a polynomial, it's a series So this is, remember, this is P of G1, sigma of G2, where G1 and G2 are correlation. Let me call it G1 and GS. So this is correlation 1 S1. So just is a property of these polynomials is that this is sum over k, phi k, sigma k, s to the k. This is something that, it's just a Hermite polynomial diagonalized. We analyze the harmonic. Okay, so if I do that decomposition, epsilon dt A will be the sum of A, and then there is the V, okay, so sigma K SP, and so let me pull it out. So the similar decomposition holds, of course, for U, where now you have sigma squared. So this is this, and then for V there is the pk, and for U there is minus sigma k integral, and then there is the S bar, just S of U, forget thing, and the TS, this will be sum over A, that is like the A back to S squared, and then sum over A So the k is because I'm taking derivative here, and then s to the k minus 1. And then here there is just a k, then there is the k integral. Yes. So I brought just the same equations using the orbit.
And the last one is take from 1. The sum starts from 1.
Yeah, the sum starts with 1. Thank you. Now, what happens is very clear, right? It's very clear. I don't know if it's very clear, but because I was, but at 0, I start with s equals 0. And so you imagine at the beginning, s is very small, right? And so when s is very small, these terms have very different sizes, right? So at the beginning, only the first term will matter, and then other terms come and kick in and becomes more important, right? Okay, and the separation becomes stronger. Now, the model for which we do the analysis rigorously is the model in which only one of these terms exists, and we start with the initialization that we expect from the previous stage. You see that that we can analyze completely. In general, we have to match things. Okay, so let's see how things work, starting from the beginning. So at the very beginning, what happens is that this A will evolve much faster than this, right? So this suggests, so A will evolve on a time scale of order 1 over epsilon. So this suggests to define a first time scale T0 to be T over epsilon. So A evolving in a time epsilon, speed 1 over epsilon, right? So this means that dt0 is epsilon dt. Right, and so we do the setting, and then we say, okay, on this time scale, I'll say that AT will be some A0 of T0 plus order epsilon. Okay, and the same for ST will be S0 T0 plus epsilon, something like that, right? Now, if you substitute this in here, you see now this is just the left-hand side is just dt0 a0 plus higher order terms, and then let's look at what are terms that are of order 1 on the right-hand side. Well, the only term that survived the term order epsilon is of course the term k equals 0, because even if I put here a 0 that is of order 1, this will take as 0 at the beginning is 0, right? The time of order epsilon will be of order epsilon, right? So the only terms that survives is sigma 0 times phi 0 minus sigma 0, and then the integral is integral of A0. So this is very simple, and T0 S0 is equal to okay, it's 0, right? because there would be an epsilon on the right hand side that comes through the derivative. Okay, so this is simple enough, right? This is basically saying that you see you can write an equation for this integral that is the projection of a on the one function, right? If you integrate this against omega, you obtain that this projection evolves so that this matches that. F0 doesn't evolve on this scale and is 0. If I call this 1 A0t, this is the scalar product of of the function 1 and A0. This will be e to the minus sigma 0 squared times t times 1 A0 0 plus 1 minus sigma 0 squared. Now sigma 0 squared comes with the product times t E0 divided by sigma 0. Okay, so very quickly, I mean, in time scale 1 over sigma 0 squared, so this is always T0. In each time scale, you converge exponentially fast. These second layer weights are evolving to match the constant part of your function. Your function after this, you are not changing anything. You are changing just the constant. Sigma 0 is the constant coefficient in the development of sigma. You're changing your weights in the second layer such that this matches the constant part of your functions.
Is it possible to have sigma 0 equal to 0?
Yeah, so good point. So here, this analysis that I'm gonna do, I'm gonna assume that things are generic in the sense that all the sigmas and all the phis are different. Yeah. If one of them skipped, then this will be the one. Okay, so this is the very first time scales. What happens later? Well, later, let me tell you a shortened story, not go through the pain of very possible calculation here. But in general, we will have a sequence of time scales indexed by L. L will be 0, 1, etc. And on time scale L, you will learn degree L component of the target function, so basically the phi, and the time scale or ansatz will be the time scale to redefine t to be a constant, so you have to center it UL plus tau, so this is a time, so this is a constant, it's just a shift, and then there is a time parameter times epsilon mu L, where mu L is bigger than mu L. So this means that this guy is much smaller than this guy. So basically what I'm looking at the time here epsilon to the mu L, and then taking a small window from bit of size epsilon to the mu L. Okay, and I'm looking at what happens here. Okay, this is my L scale. And then there will be L plus 1, so the mu's are increasing and the mu's are increasing, so epsilon mu L plus 1 will be down here, and there will be another window, etc. So things happen, in relatively small intervals. Now, all of this is small because epsilon is small, but that is a bit arbitrary, right? But what is important is that the phase in which things happen are separated by long gaps in which basically nothing happens. And So this means also that dt is equal to epsilon ul tau. Okay, and A is equal to epsilon to the minus. So in this case, what happens? So here on the first phase, what we said so is that A moves on an amount of order 1. At later time scales, what happens is that A evolves changing by big amount, and S changes by a small amount. Despite this, the amount changes matters. Right? So now what I want to do is just back of calculation to show that this gives you something, that you can treat the exponent in such a way that things match. Okay, so let's look at the first equation. So I'll write just the powers of epsilon here. And I'll only use the L term on the right hand side. All the others don't match the left hand side. So I'll match the left hand side with exactly the L. On the left hand side we have epsilon, and then the dt is epsilon to the minus ul, and then the A is epsilon to the minus omega L. And the right hand side, so this must be of the same order as, so we have S to the L, okay? So this will be epsilon to the L beta L, right? And this guy must be of order 1, okay? So let me write it as 1 minus, and then there is A, that is epsilon minus omega L, and then S to the L, epsilon to the L. Okay, and for this, dt is epsilon to the minus ul, and then AS is epsilon to the beta L, and this is to be of the same order as, there is a factor A here that is epsilon to the minus omega L. As I told you, this 1 minus n square, remember, I didn't remember whether there is a square root, but doesn't matter because in this case, S stays very close to the equator. So you have this, and then there is, this is S to the L minus 1, so epsilon to the L minus 1. Then again 1 minus epsilon to the minus omega L as epsilon to the L beta. And now, so this will all work out if I can choose this exponent, so that this must match this. So that this part is not trivial. So this means omega L. This is one equation, and then once you get this must match this. So 1 minus mu L minus omega L must be equal to beta L minus mu L equal L minus 1 beta L omega L. Okay. So this is the sequence of exponents that L equals 1 over 1, mu equal 1 over n plus 1, and omega L, well, 1, 12, L 12 plus 1. Now notice that for any L at least 1, new L is bigger than new L is bigger or equal than new L, or new L is bigger or equal than 1, and is strictly bigger for L bigger. Okay, so the picture is what I said. So these are big shift and then same. Right? And these are all positive, so what I was saying before confirm that is this guy, these weights move a lot, this weight move little, but they move in a lot, that is sufficient. Okay, because eventually you learn the whole. So again, the part that we can prove rigorously of this is, we assume that things are so one question here that you ask is how do you get this, right? Because these equations don't involve. You have about to ask. Yeah, so that is that comes from the matching with the previous time scale. That comes from matching. You have to solve. You have to solve the equations within this time scale. You solve the equation. Okay, once you find this, how do I find which one? You have to solve the equations within this time scale. You solve it within the previous time scale, and then you match the asymptotics of this to the asymptotic of that. Yeah. So the part that we can rigorously of this is assuming that things use as expected until this time, and somehow now you initialize with a generic initialization here, and then you solve the next step. And then you put only one term, you drop all other terms. Healthy expansion. Okay. So when I think of this solution is that it shows in a clear way a couple of phenomena that are observed empirically, even we see it in a cartoonish way, and it's not obvious that this is really the right explanation for those phenomena, but we see them very naturally. One is the plateaus. Each of these time scales, you get that the risk scheme is almost constant. And we see incremental learning. In the sense that at each time scale you learn a new degree of this expansion.
Yeah. So in this terminology, I get when I've seen what you do. But no, but I'm asking because I guess that when you train something, you don't have deception. Update everything is speed.
Well, it depends. It depends a little bit, right? Because you don't, but you also don't normalize most of the time things that you normalize the second layer weight as 1 over square root of n. So you initialize them. So when you the standard things in Python would be that you parameterize the network like this, and then you initialize with the AI 1 over square root. Right? Now a change of order 1, while here I'm initializing it, I'm parameterizing it like this, and I initialize with the AI of order 1. Right? So a change of order 1 here is a big change here. Right? These guys actually are updated a lot in this parameterization. This is one first thing. So actually this epsilon, now we don't do the analysis like this, we don't do the analysis like this, we do it like this and then set epsilon 0, but it might be that, I don't want to commit myself, but it might be that that captures something to be explored. But the other question is, the other point is that, yeah, you don't have this epsilon, but also yeah, perhaps that is all. I mean, there is another issue is that you don't have epsilon, but this epsilon. Suppose that now we want to do the expansion. Now here I'm assuming that there is the limit function. But if they are 0, you stay around 0 for a while. But you don't start moving unless you find a dimension, right? So now you have to put for that case, you have to put the final dimension back. So now you have a 1 over square root of the parameter that plays a role similar to that. So these are two things to be explored, but I think it's the same.
Sorry, naive questions. Maybe you already answered, but if you want to go, I mean, you have this, say, ideal system in which you have a continuum number of neurons, but the original one was with a finite number of neurons. So here you are studying the time evolution. I wanted to understand where your model breaks down. I mean, on large time or on short times. I mean, where you start to see the fact that their network is
finite.
Is finite.
Well, I think you will see it at large times.
Right? At large times.
So if you remember, the error in this approximation is the constant dependence on the errors in the number of neurons over square root of x. Right? And so how this constant depend on t, well, it's exponential in t, right? So this means that I can cover finite time or a logarithmic n times, but after that, on the other hand, here, as you see, you converge on a time of order 1 in the dimension, for instance. So, I'm relatively happy, right? Now, what happens at large time? If you remember the way we really use the fact that this large dimension is that we can replace each neuron. I mean, you can use this spherical symmetry, right? So essentially what we use it for is really where we use it for is in doing this. There are the scalar products, and the risk and the evolution depends on the scalar product and the interaction between two neurons, right? And where we use really the large end is we replace this as the expectation of we replace so the only part where you really make a mistake is in writing this as expectation of u as I as j. So, okay, let me do this. So this is the interaction between two neurons, right? And okay, this is of course always equal to, let me call them u1 and u2. There is always a term that is S1, S2, the projection around U star, and then there is a term that will be U1 perpendicular, U2 perpendicular. Right? And let me normalize this guy. There is a piece that is always 1 minus S1 squared, 1 minus S2 squared times U1 perpendicular, U2 perpendicular squared by its norm. And if you remember what I did is that I replaced this by an expectation over U2 perpendicular uniform on ST minus 1. And these are, let's say, you can think of these as T minus 1 dimensional vectors. Right, this is where I used it. In other words, if you look at the slice S2, and really, this is, so this replacement, happens because in the slice S2, there is a bunch of other neurons that take projection with U star. Here what I'm drawing is the unit sphere. This is my direction U star. There is a bunch of other neurons that have the same projection S2 with U star. And when I do the scalar product U1 with all of these neurons, I can replace the sum over all of those neurons by just a uniform integral. And so there is sufficiently many neurons in this slice that things work. Not scary. So it might be possible to this part CFT. Okay, so perhaps I'll take a few minutes of pause and then the last part of this lecture, what I want to go. So this is one example, a simple example in which one thing that happens is what's called people call feature learning. That is, you learn some low-dimensional representation of the data. Is a very primitive example of that. This is something on which there have been a number of papers over the last year. So I want to kind of an overview of a subset of this result. So we started. So what I'll do as the last part of this course is give a little overview of a few other results in the feature learning. And I will really, so this will be very short review. Then we really, give an informal account of results from only 3 papers that in more, of course, than 3, but it's 3, diverse set of okay. The first one is by Al. They're all 2022, so let's review the 2201. Try to write things in the same setting for all of them. But the settings are pretty general, but there are pairs that are different. So this is 2 layers network. Normalize it one by one square of n. And I'm gonna write it also as 1 of P transpose P hash, where W is D by capital N, or and they look at square loss. And so this is similar, apart from the normalization from what I was saying. What's talking about, and the assumption on the data distribution is again very similar. Psi Gaussian, this is the same. Yi star plus noise, right? And yeah, again, let's say that. So not much changed, and the initialization is this is again similar to what we were doing. One difference is that they take the initialization of the AI to be not much. Actually, if you think about it, it's not different either. Okay, it's not different at all. So if you look at the 1 over square root of n AI, this is 1 over n. So what is the algorithm now? We look at the different type of algorithm. They do one step of gradient descent. On the step theta. Where G0 is the gradient. They do one gradient descent with respect to the first layer. V0 is the gradient. And after one step, the second thing that they do, that they use draw new data. x by tilde. So this is full batch gradient descent. They take the gradient with respect to everything in one step, then they draw new data and only fit the second layer. Using ridge regression. So it's a two-stages algorithm, in which the first stage you just do one step of gradient descent, and the second stage you fit the second layer. And okay, so what is the interesting thing about this is that, again, if you don't do the first step, we already talked about it, and you will not be able to do anything. So they focus on this regime, on the proportional asymptotic regime. So we saw that if we do this, and if you don't do the first step, you are doing just ridge regression with respect to a random feature. So you cannot do much. You cannot only ridge regression. We call it, we saw already that the risk, the test error is lower bounded by the projection of F star onto polynomials of degree at least. So now when they have two results, first, they analyze the case in which this step size is about the 1. So step size of order 1 means that the operator norm of this gradient is the same order as the operator norm of and what happens is that they compute exact asymptotics in this regime, and we show that you get an improvement over random features. So this is random feature model. We just fit ridge regression with respect to feature, so you get an improvement, but still lower bounded by okay, so you don't really beat these curves. So you have sample size divided by dimension. Here there is this lower bound, plus with this method you get a curve that is lower, but still cannot beat what you achieve in the linear. On the other hand, they show that make the step size be much larger, the step much larger. So this means what? This means that the Frobenius, and this turns out to be the scaling in which the Frobenius norm of this guy is of the same order as the Frobenius norm of this guy. So basically you are changing every weight by an amount of the same order as the weight itself. Then in this case, in the first case they get exact asymptotic. In the second they get only bound, but they get a bound the form. So the bound is the form something like so here to star is some distance between a sigma and sigma and phi are same to star is 0, so let's neglect for the moment to star. So this is a floor, But apart from this floor, this is going down to 0. In particular, in general, it will beat this floor. So this method beats just random features or model. Okay. The reason you get that by just doing one big step. One big step of gradient, and you can beat the. You can exit the neural tangent. And here the intuition is quite simple of how this happens. But the point is that as soon as you get a non-trivial alignment of, this is an easy calculation, if you get a non-trivial alignment of the Wi with the true vector, right? So if, for instance, you take, the intuition, so part 1 of the intuition, if the Wi, instead of taking at initialization uniform on the sphere, if I took them, let's call it Si times W star plus W perpendicular I, so instead of taking uniform on the sphere or Gaussian, you take them with some non-trivial projection on W star, Si 0, then you are in good shape if you just do kernel, the kernel method or random feature method with respect to some such a network, then you can of course fit one that can be in fact can be consistent, right? Okay. Intuition number 2, if you look at the form of the gradient, if I compute the gradient with respect to Wi of I, what is this? This is Yi minus F I. And then there is the gradient of the function. So this is Ai over square root of n linear normalization with respect to Wi. So there is a sigma phi of WL psi. Then there is so if I for a moment neglect this piece, because at initialization the function is small, so this should be about AL, coefficient times AL, and then there is sum over I 1 to n, 1 over n, and then there is Yi xi times sigma prime of WL times xi. Like this thing, this should be about AL 1 over n sum over I apart from constant sigma I xi. And this should be the same as the expectation of P of W star x, and x just by law of large numbers. And this expectation just by rotational invariance is just W star times the coefficient. Okay, so what I get is that the gradient with respect to WL R hat n will be about some coefficient times AL W star. Okay, so basically the first step of the gradient moves each weight in the direction of W star. So this changes just by doing the first step of the gradient. Another way of seeing it is that if you look at the whole matrix gradient, there should be some coefficient times A times W star. So basically, if you look at the matrix of weights after the first step is just a rank 1 perturbation of the original matrix. And the rank 1 is the direction of W star. Yeah, so this is about that. So this is why I gave you two step sizes, right? So this step size, is such that eta times square root of n times the gradient about the one order of the same of the operator norm of W. Which is, again, this is square root of capital A. From this you can work out the constant. So, but the point is that this case instead the Frobenius norm, and these two are very different because the gradient is rank 1, right? So for W, the operator norm and the Frobenius norm are very different, but for gradient, the operator norm is different. So this is I think it's nice because it's really explains this. It's some simple case in which you get features learning very quickly, and this can happen very quickly. An interesting fact. So the second paper is Damian. So here there is some small changes in setting. Now my class of function is this one, and so they just have a case in which this is Relu. But looking at their proof, this doesn't seem to be exactly simplifies some calculation. And the data is distribution is x side the same as before, and yi. But now the ZIs are not a specific model, but well, this is uniform plus or minus 4. I don't know exactly why, but I think again simplify the calculation, and then at tau x is u of u transpose times x, where u is u is an orthogonal metric. So u is d. So this doesn't depend only on one-dimensional projection, but on a general k-dimensional projection of the data. Okay. So it's a more complex model, and they assume P to be a degree of freedom. What is the algorithm? Okay, so they initialize with A0I plus minus 1 WR is the same. Essentially, and BI to be 0. And okay, I will not write it, but specifically, but already talked about it, they initialize it in such a way that at time 0 is equal to 0. Basically, they are an even number of neurons, and we set up things in such a way that the second half of the neuron cancel exactly the first half with this coefficient. And then what they do, okay, they have a first step in which they subtract the mean and the linear trend from the data. Compute the mean, the labels, and the linear coefficient of the labels. They don't want it. But then they, in the first step, do yi minus alpha minus beta times x. Okay, so think of it as they really are interested in the case in which the linear component and the mean of the vector star is 0. They are really interested in this case. So the mean of the function is 0 and the linear component. If you do that, then you don't need this step. But with this step, you can always reduce yourself to this case, okay? Because this should be about the expectation of the star of x. It should be, this concentrate around. And so instead of, they say, okay, if I can do this case, I can do the general case, but subtract. So now, in this case, what they do is that they do again a single step of gradient descent. But they do it in a peculiar way. Don't add it to initialization, they just compute. They just compute. If you look at the previous paper, it's clear that the gradient contains information while the initialization doesn't. Say, okay, let's throw away. Now, it's a bit, between the lines. It's written in a way that you have to read it to understand that this is what they're doing. Because the way they write it is, okay, they do W0 minus eta times the gradient, and then they say we do some weight decays. This is equivalent to regularization, right? To do this, it's like putting a range regularization down, right? This machine learning language is called weight decay. So when they say we do gradient descent with weight decay, but then if you look at the theorem, then they say eta times lambda equal to 1. So this is in fact what
K here isn't the one.
sorry?
K is
Yeah, K, okay, I'll state the result. It can grow, but yeah, think of it as a small, but it can grow. Doesn't mean, I don't think they're about. And then 3, after you do this, you reinitialize. So at the first one, I put b equal 0, and I do this with b equal 0, and then I reinitialize the bj normal 0, 1, d, but then you don't do anything with that. You fit range regression with respect to the second layer. With respect to your AI. So in a way, it's very similar to the first scheme. Is very similar to the first one. You do one step of gradient and then the range regression. The real difference is really that we are looking at, there are some twists in sense that this is a polynomial, but this is higher dimensional class of function. And they are not using the linear. If you look at what the argument in the first paper, it was very important that this was non-zero. When now they are not using this at all. Okay, so let me describe the result of this paper. They have also other results, but the main is lower bound. But let me describe the main result of this paper. The assumption, one of the assumption is that you look at the matrix of second derivative of the target function, the expectation. And so here, this is the Hessian of the target, and you take the expectation of the Hessian. So this is a D by D matrix. But since I started on the so this is the expectation of the matrix, the Hessian matrix of P transpose times X. This is so you can understand this. This is U times a matrix U times U transpose. This has a rank K. Okay, and what you have assumed that lambda K. Okay, so the K eigenvalue of H is bounded away from 0. Now they don't assume that this is of order 1, but for simplicity here I write things as if it was of order 1. So the Hessian, the span of the Hessian is really the U, the subspace U. So if I, in particular, if somebody gives me the Hessian, if I can deviation of matrix, then I can estimate the subspace. There are actually papers. Actually, I brought it years ago. So one way to estimate U is to take the sum of I. Now something like Y and something. If you take this matrix, then from this you can figure out the space U. But they don't do that. So this was a paper with Stratis on this. Myself, okay, it's a standard thing. So they don't do that, but they assume it. And then under this assumption, so they say, okay, if this is bounded out from 0, then you can estimate the subspace from the subspace from H. And basically all the name of the game is showing that if you compute this guy is basically identifying it is proportional to this Hessian. And the result that they get is that if n is much bigger than k squared, then this risk so this means up to constant. Okay, so okay, let's forget for a moment this condition. So, let's not forget. So this requires, for being small, that the network size is much bigger than k to the L. If you remember, so where does this come from? So this comes from the random feature model in k dimension being able to represent polynomial of degree L. So this is something that we saw already in the case of random feature. And what is the other condition? The other condition is that the sample size is much bigger than b times k to the L. This is basically the condition that, the same condition if you are in dimension k, that you can fit polynomials of degree L by using, for instance, random feature models or kernel-rich regression, etc. Okay. Now this extra factor d, this is probably an artifact of the proof. And the last condition is that so basically, morally, this is saying, apart from this spurious factor, this is really, what you need to be able to estimate the Hessian. This is what you need basically to be able to estimate subspace. So what they are saying is that once you estimate the subspace, modulo this factor, this is like doing, kernel-rich regression in dimension k instead than on dimension d. It's a very big difference. Okay, so where the intuition of how the proof of this goes. I say, okay, let's compute what I brought before, the gradient of the infinite space. Okay, this is proportional to encryption. This is exactly what I wrote before. Right, and then this is 0. They set things in such a way that this is 0. So this should be, it will be 1 over n. This will be 1 over n, but let's say L, so this doesn't really matter, times 1 over n, sum over I 1 to n, then yi, and then sigma prime of wi. You say, okay, for log n, it should be about a L times the expectation of x star of x times sigma prime of wl times x. And okay, before we were assuming that x star has a non-trivial correlation with x, so you get the expectation of this guy has the correlation between these and if this doesn't happen, then okay, one way to do it is integrating by parts, right? So integrate by parts Gaussian. Can integrate by parts. The dominant term is the one in which you. And on the thing, another way is to do expansion in Android polynomial. So, in particular, this in the case is particularly simple in the case of value because now this becomes x indicator wl x. You get 0 times x. Okay, so I claim that if you do any of these things, you get this al this Echelon matrix dash wl. And now what they say is okay. So that before we had the lower order term, now they say, well, if I now take wl at random, now h is u times the matrix times u transpose. So the overall gradient takes this form, and if I take w at random, this will be u times some matrix m. So it will be able to span, infer all the, to span all the space here. Right, so the weights will align u and they will span the whole space. Okay, just 5 minutes. Last paper I want to mention is a Bethel 2022. So all of these papers appeared in the span of 3 months. Okay, so what is really interesting about this paper and different from the others? One that we mention is the data distribution, the assumption on the function class. Well, the X is a bit different, it's simpler, it's uniform on the Q. So far we took something spherical, symmetric. Now we take uniform on the cube, and really the advantage of this is that makes Fourier analysis. Yeah. The spherical harmonic, you just have polynomials. Okay. Now you take the function to be, so any, again, yi is star of xi plus noise, and the function, any function x star, you can do Fourier analysis. So Fourier analysis of an Andrea cube means that you decompose this into polynomials. The Fourier basis over the hypercube are just the monomials. Okay, so FX is here. And you should think of this as analogous to the composition that we did in spherical harmonics of the sphere. Now, for any such function and for any such, you can define, let me call it this bold S of S star. This is the set of subset such that F S is different from C. So what are the Fourier coefficients that are known here? Okay. And we say that F star has the merged staircase property if the following happens, if there exists an ordering S equal S1 to Sn. So you can order this Fourier coefficient, the non-zero Fourier coefficient, such that for all I less than infinite, what happens is that Si minus the union of F3 1 to N1 of F3 Si is at most 1. Okay, so for instance, F star of X is 1 plus x1 x2 plus x2 x3 4. This is an example of a function that has the merged staircase property. Simple, because if you order them in this way, this has only one term that was not here, this has only one term that was not here, and this is only one term that is not here. So, of course, if you take just this polynomial, this monomial, that's better. And the main result of this paper they also have lower bound that match this upper bound, but the main upper bound result is that if X star is SP, then the two layers neural net are large enough. And large enough. This is the number of neurons. order the samples. This is, yeah, here it's yeah, okay. No, I don't remember. It's compressed, but I think this is holds for any, so this is holds as long as the maximum Fourier coefficient of the total support has some bounded size. Right? So this must contain more than one number of terms. But what is nice is that you get order these samples, while if you add only this term, you get polynomial. And the way this works is that basically you learn various coefficients in the order in which a bit similarly to what we saw. And one nice thing about nice for me about this is that they use for proving this, as you see from this end now, they use reduction in field theory and reduction to lower dimension. Let's use the fact that this function has finitely many components to reduce the mean and description P to a finite dimension. Okay. Any question about this? If not, I think that's all. Thank you.
Thank you.